Hello and welcome once again to my channel. In this video, we'll be looking at action potentials. Action potentials is defined as a change in the charge of a neuron or muscle cell. Now, this video will be useful for students studying AQA A-level biology and those studying the applied science at BTEC. Now, on the graph, which is a typical one they use to demonstrate what happens during an action potential. So on the graph, you have the resting membrane potential. It's normally at around minus 70 millivolts. The threshold that is after a stimulus has been detected is about minus 55 millivolts, and it peaks at around plus 35 millivolts. Once a stimulus has been detected, you have a process called depolarization taking place. And that's where the voltage-gated sodium ion channel open and sodium ions rush in. Depolarization is where the neuron becomes less negative and more positive. And then, once it gets to the peak, sodium ion channels will begin to close and potassium ion channels will begin to open. So once again, it generally peaks at around 35 millivolts. After that, repolarization takes place. Now, in repolarization, this is where a neuron's membrane potential returns to its negative resting state, which occurs after depolarization. Now, in repolarization, it occurs once again when potassium ions leave the cell. And once that happens, the potassium ion channel will close, but not very fast. It happens slowly. Then it returns to the resting potential, but it sometimes shoots past the resting potential, and then you have another stage called hyperpolarization. Now the next stage, from the peak all the way down the center of the graph, so between depolarization and repolarization, you have the absolute refractory period. Now, the absolute refractory period is the time during and immediately after an action potential when a second action potential cannot be triggered, regardless of the strength of the stimulus. Now, in this next section, we will look at the cell membrane of a typical neuron, and we'll look at the voltage-gated potassium ion channel, voltage-gated sodium ion channel, and the sodium-potassium ion pump. So we'll see how these different sections of the neuron operate during an action potential. Okay, so here you have the voltage-gated potassium ion channel, then the sodium-potassium pump, sodium-potassium ion pump, where 3 sodium ions are pumped out and 2 potassium ions pumped in. And then, of course, the channel for potassium ions where it is pumped out of the cell as well, or out through the membrane. And so you will have a large number of sodium and potassium ions inside and outside the neuron. And then on the last section, you have the voltage-gated sodium ion channel. So the sodium-potassium pump actively transports sodium ions out of the neuron and potassium ions into the neuron throughout the action potential process. Now I'll do a quick summary of the whole process. So if the diagram was a bit tricky to make sense of, here's a lovely summary of the action potentials process. So the first stage of an action potential is depolarization. This begins when a stimulus causes the membrane potential to rise from minus 70 millivolts to the threshold value of about minus 55 millivolts. Step 2, this triggers some voltage-gated sodium ion channels to open. Sodium ions then diffuse rapidly into the neuron down the electrochemical gradient. This influx of sodium ions causes further depolarization, which opens even more voltage-gated sodium ion channels. As more sodium ions enter, the membrane potential rises to about plus 35 millivolts. At this point, the voltage-gated sodium ion channels close and becomes inactivated. Step 3. The voltage-gated potassium ion channels open, increasing the membrane's permeability to potassium ions, and these diffuse out of the neuron down their electrochemical gradient. Step 4. This causes repolarization, returning the membrane potential towards its resting value. However, the voltage-gated potassium ion channels are slow to close, so too many potassium ions diffuse out of the membrane. Step 5. This results in hyperpolarization, where the potential difference falls to about minus 90 millivolts. The voltage-gated potassium ion channels then close, and the sodium-potassium pump redistributes sodium ions and potassium ions, returning the neuron to its resting potential of minus 70 millivolts. This action potential will be conducted along a neuron until it reaches a synapse. Thank you so much for watching, and I hope this video was helpful. Have a great day, and all the best in your exams as well.